In this tutorial, we're going to go over colligative properties. So there are basically four colligative properties that we're going to talk about. But just before that, what is a colligative property? So a colligative property is a property that is dependent on the concentration of solute particles and not on the identity. Okay. So basically, a colligative property, it is in terms of a solution. If you're talking about colligative properties, you're talking about properties of a solution. Okay. So what are we trying to say? So we're trying to say a colligative property is not going to be dependent on the identities of the particles. So for example, a very good example I can give you is boiling point elevation. So you're going to note that the boiling point elevation is one of the properties that is referred to as colligative because it doesn't depend on the identity but on the concentration. So here is an example. When you get to dissolve sodium chloride and you get to dissolve a different salt, for example, you can say potassium chloride. So you're going to find that these two are going to have the same effect irrespective of their identities. Okay, so basically when you talk about the boiling point elevation is given as the change in temperature being equivalent to a product of Kb multiplied by M multiplied by I. So where the Kb represents the boiling point elevation constant, M is molality, then I is Van Hoff's factor. Okay, so Van Hoff's factors. So now what are these? So molality is basically the number of moles dissolved in the kilogram of what? Of a solution. Van Hoff's factor is determined as the number of ions in that salt. So for example, if you try to write the formula that is dissolution of sodium chloride, it's going to split to sodium plus chloride ions. So there are two ions there. So as we get to plug into our formula, we need to know the value of the Kb of what? Of the solution that we're talking about, of course, depending on the solvent. So let's say in this case, we are trying to dissolve sodium chloride in what? In water. So water has got a Kb value of which is basically 0.51. So then depending on the molality, which is basically going to be dependent on the kilogram of that solution. Okay, so now let's say in this case what we're trying to talk about, maybe the mass is, let's say, a kilogram, right? Then we've been told the solution concentration is just 1 molar concentration. So that would entail that what we're going to have is basically just for molarity, the number of moles, because when you say 1 molar concentration, you're saying this is equivalent to, it's a 1 mole per liter. So it's like you have a mole per liter. So you plug in a single, you have a mole, then the mass is a kilogram. So basically what you're going to have is just a 1. So you plug in, then the Van Hoff's factor is going to be the number of ions, which are just basically 2. And that is how you're going to determine what? That's how you're going to determine your change in temperature or boiling point elevation. So basically that is an example of colligative property. Doesn't depend on what you've put there. It's not like we're depending on the identity, but basically we're just trying to focus on the number of ions in that salt and also its concentration. So let's try to talk about these in details. So the first colligative property that we're going to talk about is basically vapor pressure. So vapor pressure. So what is vapor pressure? So when you're talking about vapor pressure, you're trying to talk about how easily particles of a solvent can escape to the atmosphere. How easily can they escape? Okay, so vapor pressure is basically dependent on this formula. Okay, so the vapor pressure of a solution denoted by P solution, is basically equivalent to what? To the mole fraction of a solution, or rather a solvent, multiplied by what? Multiplied by the vapor pressure of a solvent. So now we need to understand what this formula means. So of course, in terms of a colligative property, we're talking about the solution. That's what we're interested in. We're interested in the solution. So now what is going to happen is this. As you get to multiply the mole ratio, the mole fraction of a solvent, multiplied by the vapor pressure of a solvent. So now understand that in your calculations, the vapor pressure of a solvent, of course, which is a liquid, is going to be given. Then for a mole ratio or mole fraction of the solvent, it's like you're trying to compare the number of moles of a solvent in the total number of moles in that solution. Okay, so therefore what we can say is the mole fraction of a solvent, so we're saying this is a mole fraction. So it's going to be the number of moles of the solvent, of which in most of the cases is going to be water. So you can say the number of moles of water, which is the solvent under study, is going to be divided by the total number of moles of what? The solvent and the solid. Okay, so say the number of moles of the solvent water as well as what? The solid. So that is going to give you the mole fraction of the solvent in that case. So if you've determined now your X solvent, which is basically the mole fraction of a solvent, comparing the number of moles of a solvent to the total number of moles in that given solution, that is what you are calling your what? Your X solvent or your mole fraction. So after you've determined your mole fraction, you can plug in the formula and multiply against what? And multiply against the vapor pressure of a solvent. And basically what we're trying to say is, if you compare, it's like if you increase the vapor pressure of a solvent, the higher the vapor pressure of what? Of the solution. Now what is the funny part is, we're trying to study the effect of you adding a salt to a solution. So it's like if you increase the concentration of a salt, it's part of a denominator of the solvent. So what happens if you increase the number of moles of salt in a solvent? What is going to happen to the mole fraction solvent? What is going to happen? So understand this. Let's have a practical approach. Let's say we had maybe then the number of moles of water being equivalent to, let's say, 1. Then you get to have the number of moles of the salt that is under study. Let's say it's also a 2. So understand this. You're trying to determine the X solvent, which is the mole fraction solvent. You're trying to compare the number of moles of what? Of the solvent itself over the total number of moles in that solution. So this is going to be 1 over what? 1 over 3. Now what happens if you try to increase the number of moles of the salt? What happens if you make it 3? So you're going to have 1 plus, or 1 over 1 plus 3. It's going to be 1 over 4. So now the question is, which one is bigger between 1 over 3 and 1 over 4? So the bigger value there is what? Is 1 over 3. Meaning that if you increase, so what we're trying to say is, you increasing the mole fraction, or you increasing the concentration or the number of moles of salt, or we can say the concentration of the solute, or the number of moles of salt, is going to reduce what? This is going to reduce the vapor pressure of the solution. So the higher the concentration of the salt, the lower the what? The lower the vapor pressure of that solution. And if you add less of the solute, which can be a salt, it's going to be easily lost to the atmosphere in comparison to a solution that is adding a lot of what? Or a higher concentration of the salt. So that is what we're trying to say under what? Under vapor pressure. So understand that vapor pressure is basically of a solution is given as the mole fraction of a solvent multiplied by the vapor pressure of the solvent before addition of a salt. Now, the other property that we have to understand under corrugative properties, we need to understand basically the concept of osmotic pressure. So, how is osmotic pressure a corrugative property? So, osmotic pressure. So, we need to understand that osmotic pressure, denoted by pi, is basically given as a product of mRT. So, now you need to be careful when you look at the formula. So, unlike the other part which we're going to talk about, so this capital M denotes molality, okay, which is basically given as what? The number of moles dissolved in a liter of the solution. Okay, very important to note that. Then the other there is our gas constant, which is basically equivalent to 0.08206. That is L ATM per what? Per mole per Kelvin. So since our gas constant is given in Kelvin, we need to note that even as we get to do with our calculations, our temperature should also be in Kelvin. And our temperature is basically, our temperature in Kelvin is basically your temperature in degrees Celsius added to 273 degrees. So what you're going to have is the answer in Kelvin, just in case you forgot that. So we know what these letters represent. Of course, the I there denotes the Van Hoff's factor. So we've talked about how to go about the calculations there. So now what happens? So what you're going to notice, the higher the concentration, what happens? Even osmotic pressure is going to increase. So unlike in a case of vapor pressure, which is kind of inversely proportion, this one is direct proportion. If you increase the concentration of a salt, basically the osmotic pressure is going to be higher. Okay, you increase the temperature, it will be higher. Of course, the Van Hoff's factor is dependent on the ions, of which I've shown how to do the calculations. Well, okay, so this is a corrugative property. It is not dependent on the identity, but it's just dependent on how much of each solid that you may have. It may be sodium chloride, it may be magnesium chloride, but we are not interested in the identity. All what we're saying is its effect is going to be dependent on its concentration. And that's why osmotic pressure is what? Is basically corrugative property. Okay, so the last two, let me go back to the boiling points. Boiling point elevation. So we were saying boiling point elevation is what? Is a corrugative property. So boiling point elevation. So when you're talking about the word elevation, it means you're going higher. You're increasing something. It's like an angle of elevation. You try to look at something that is higher than you. So that is an angle of elevation. Depression means going down. Okay, that's what we're trying to say there. So now let's try to explain this in more in detail. What are we trying to say? So if you look at the formula of boiling point elevation, which means that the boiling point is going to be higher, it's basically equivalent to what? To the boiling point elevation constant multiplied by the molality multiplied by the Van Hoff's factor. Okay, so now Kb is going to be given as a constant. Of course, you need to note that for water, the Kb value is basically equivalent to 0.51. Okay, then what else? Molarity, this is a small letter m, which denotes that it's basically the number of moles dissolved in what? Dissolved in a kilogram of a solution. That is what molarity means. The Van Hoff's factor said you determine the number of ions that are in that salt. Okay. So for example, for sodium chloride, we said this is going to be sodium. So there are only two ions that we're talking about in this case. So therefore, your Van Hoff's factor is going to be what? It's going to be a 2. And that's what we're trying to say. So what is how you get to determine the boiling point elevation? It is only dependent on the factor, the boiling point elevation factor of the solvent that you're talking about, the molarity, which is basically one way of expressing your concentration. So it is only the concentration that is affecting. It is the concentration that is affecting what? The boiling point elevation. So what basically we're trying to say? So what we're trying to say is if you get to do some calculations, you try to do some calculations, you try to deal with different concentrations. For example, if we talk about the sort of, let's say sodium chloride, we use the 2 molar concentration of sodium chloride. What is going to be our boiling point derivation in such a case? So a boiling point derivation is going to be, of course, our Kb said is 0.51. Then the molarity in such a case, depending, assuming our mass was a kilogram for the water that we have, it's going to be 2/1. Then our Van Hoff factor is a 2. So what happens if you get your calculator there? Get your calculator as 0.51 multiplied by 2 multiplied by 2. So what I'm getting at the boiling point derivation is a 2.04 degrees Celsius. So that's what you have as. So now what happens if we try to increase the concentration? What happens if we try to increase the concentration? Let's say maybe the molarity was the 2, or the 5. Then, of course, we know the Van Hoff factor is the same because we're talking about of the same sort. So that is going to be like 10 multiplied by 0.51. Because 5 by 2 is a 10, so we have 5.1 degrees Celsius. So it's like the more of a sort you had, the higher it will be very difficult actually for you to do what? To boil that solution. The more you add this, the more the concentration of the salt that you had is going to be very difficult for the solution to vaporize. That is what we mean by boiling point derivation. You increase, it has got an effect of increasing what? The boiling point of the solvent. Okay. Finally, let's try to talk about freezing point. Then just before I get to move on to the freezing point depression, I need to emphasize on the formula. So what I'm trying to say is the change in temperature. So there may be some cases where they tell you what is going to be the boiling point. Maybe they've given you the Kb, they've given you the concentration and the Van Hoff factor, depending on the sort that they've given you. Then they ask you to determine the boiling point. What is going to be the new boiling point after adding a salt to a solvent? So you need to understand that this change in temperature that we're talking about is basically the final temperature, or I can say the new boiling point. It's basically the new boiling point minus the what? The initial boiling point. Okay. So that's why we're saying it's a change in temperature. So it's like the initial temperature, the initial boiling point of the fluid changes. So the new boiling point is going to be equivalent to what? It's going to be given as the initial boiling point plus the boiling point derivation. It's like you get to add it. The boiling point derivation should be added to the initial boiling point for you to be able to determine what? For you to be able to determine the new boiling point of a solution. Very, very important. Don't be confused. Okay, then finally, what you're trying to talk about is now the freezing point depression. Freezing point depression. So here it's kind of different. Instead of it being elevated, it's depressed. Like it becomes lower. Okay. So the formula is given by the boiling point depression. We want it to be a positive value, so the formula becomes the negative Kf, which is basically freezing points, freezing point depression constant, then multiplied by the molarity multiplied by the high. That's what we get to have in such a case. And therefore for water, freezing point depression factor or constant is negative 1.86. That's what we have. So that is like degrees Celsius per concentration. So degrees Celsius per molar concentration. So remember, this molarity of ours is basically given as what? It's basically given as the number of moles dissolved in a kilogram of what? A solution. So what happens under this colligative property? It is also dependent on the concentration, Van Hoff's factor. So what is going to happen is that if you increase the concentration of a salt, If you increase the concentration of a salt, it's basically going to affect what? It's basically going to affect the freezing point depression. So if you increase the concentration of the salts, what are we trying to say? What we're trying to say is the temperature is going to be lower. The temperature is going to be what? The freezing point is going to be lower. That's what we're trying to say. And this explains why in most of the countries where you find that usually when it's a period where snow is where there is snow on the roads, they want vehicles to be moving around. So what they'll do is they'll add salt to such roads to avoid the snow freezing. Because like if you add salt to the snow, it's going to increase or rather reduce the freezing point, meaning that it will require a very low temperature for the liquid to do what? To get frozen or to solidify. So basically these are the major corrugative properties that are in existence. I just hope that you've gotten ideas about them, and watch out for the next video where I get to look at a lot of practice questions on corrugative properties. So thank you very much for watching.